All right, so this is our first lecture video for the support course, Maths 40, the support course for Math 340. In the parent course, Math 340 this week, we're covering exponential and logarithmic functions. And the purpose of the material we're going to cover now is to try and work on some prerequisite stuff that's going to help with what we cover in that class. So to start with, we're working on exponents and radicals today, and all I want to do is cover these properties that exponents and radicals have. You learned this in an algebra course, and then use these properties to either simplify or expand some different expressions that we're going to encounter. The assignment that you're going to do for this week is going to just be a bunch of problems that look basically like what we're doing in the examples here. So a quick recap of these properties here. 5 properties for exponents that I want to cover. First of all, if you have x to the power of a times x to the power of b, that's the same thing as x to the power of a plus b. The key thing here is that both of these exponential expressions have the same base, x here and x here. That's critical. If they have the same base, then regardless of what these two exponents are, when I multiply them together, I can simply add those exponents. Similar for division. So if I have x to the a divided by x to the b, that's the same thing as x to the a minus b. We have a property also where if I take a product of two things, x times y, and raise that entire product to a power like a, you'll notice the parentheses here have to be there in order for it to be assumed that I'm raising the entire product to that power and not just the last part of that product. Exponents distribute over products. So this becomes x to the power of a times x to the y to the power of a. You get a similar result with quotients. So if I have x over y and I take the whole thing, so you'll need to have those parentheses there to show this, to the power of a, I can bring that a into the power of my numerator and denominator. So I get x to the power of a, y to the power of a. Finally, if I have a power to a power, so x to the power of a, and then the whole thing is raised to the power of b, that's the same thing as x to the power of a times b. So I can multiply these exponents together. Okay, those are useful properties of exponents, and we encounter them a whole lot in calculus. So it's a good review. Radicals. You'll notice in calculus, which it'll be after this first week that we really start doing this, but it's very, very helpful in calculus to think of radicals as rational exponents. And we talk about this a little bit in the parent course lecture for this week, but just to recap, if I have a radical of this form, so the bth root, this b here is just some integer, some positive integer, and I'm taking the bth root of x to the a, that's the same thing as x to the a over b. So we interpret that denominator as the index of that radical, the numerator as whatever I'm raising this radicand to. Radicand is the thing inside the radical. Okay, so for a lot of the stuff that we do with radicals, it's helpful to first convert it over to a rational exponent, and then you can use these exponent properties to do your simplifying. If you do it that way, you don't really need these other two properties because both of these are already accounted for in some of the properties we listed here. But just for completeness, I'm going to mention them here. If I want to take the nth root of a product like x times y, that's the same thing as the nth root of x and the nth root of y. You'll notice in parentheses here I said if x and y are both greater than 0, meaning both positive. And now that's not always necessarily the case. For example, if n is a 3, if I'm taking the third root of something, I can take a cube root of negative numbers. But since I'm not specifying what n is, if n is something like 2, you can't take the square root of negative numbers, not without introducing complex numbers, which we don't do anything with in this class. So this property is just, it has this extra condition on it to avoid the complication of dealing with complex numbers and things like that. Okay, we have a similar one for quotients right here. Let's go ahead and get into the examples. So all of the examples we're going to look at are going to say something like simplify or expand. Now to simplify an expression like this, it's basically just asking us to use these exponent properties up here to kind of reduce this thing down to what might be called its simplest form. So what I'm going to do first is you have a couple of approaches that actually work. You don't have to do this in the exact order I'm going to do it, but you can do it one or two different ways. So what I'm going to do is I'm going to start inside the parentheses and do any simplifying that I can in here before dealing with this second power on the outside. So here's what's going to happen. This thing here is equal to what? Well, 6 over 15, if I ignore everything else, that's a fraction, and I can simplify that by dividing everything by 3. So if I divide by 3, I'm going to get 2 on top, 5 on the bottom. Okay? Now let's look at what else we have. M to the power of 0.1 in my numerator, m to the power of 0.9 in my denominator. Ignoring everything else, if I just pay attention to those m's to those powers, I have the same base in each of those exponential expressions, m and m. So going up here, I can use this property number 2, that says I can take the exponent in the numerator and subtract from it the exponent in the denominator for those exponential expressions. So let's think about that for a second. That would give me m to the 0.1, or so, divided by m to the 0.9, and if I subtract 0.1 minus 0.9 is negative 0.8. So by default, once I do that subtraction, whatever I'm getting will automatically be right here in my numerator, negative 0.8. But we're going to move that in a later step. Okay? Now if I do the subtraction here, n and n cubed, so just looking at the n's, when you see just an n there, you can think of it as n to the first power. So if I did 1 minus 3, that would be negative 2, n to the negative second power, and then all of that is raised to the second power. Okay? Typically, when we are simplifying expressions like this, it's common to want to represent things without negative exponents. Now, that's not universally the case. Sometimes we don't really care. Sometimes it's fine to have these exponents left as negative numbers. In fact, when we're getting to chapter 2 in our textbook, when we're taking the derivatives of different functions and different expressions, it's actually better to leave these as negative numbers. But for this problem, I want to represent everything with a positive exponent. So what do we know about negative exponents? Well, they represent reciprocals of things. So m to the negative 0.8 is the same thing as 1 over m to the positive 0.8. But by doing that reciprocal, it's actually just taking the expression and moving it from the numerator down to the denominator. So I can think of this way. 2 over 5 m to the 0.8. Notice that it's a positive exponent now because I have moved it down to the denominator. That's what that negative up there is doing. Similarly, I can take that n to the negative 2 in my numerator and rewrite it as n to the positive 2, or n squared, in my denominator. Okay. Finally, I need to square everything. So in my numerator, I'm going to square 2. That would be 4. 2 squared is 4. I'm going to square that 5. That's 25. I'm going to square this. But this m is already being raised to a power, and now I'm going to raise it to another power. That's where property 5 becomes useful. So something to a power raised to another power can be simplified by just multiplying those exponents together. 2 times 0.8 is 1.6. And same thing here. This 2 times that 2 is 4, n to the 4th. And that is as much as I'm going to be able to simplify that. I could take this decimal and think of it as a rational exponent and then convert it into a radical, but I don't really care to do that. In fact, again, in calculus, it's much easier to work with rational exponents than it is with radicals, especially when we start doing derivatives of things. So that's perfect. I'm going to leave that the way that it is. Let's try another one. Okay, I want to simplify this expression right here. And again, there are different ways of going about this. So I could deal with this innermost set of parentheses first by taking this 4 and bringing it in. But I'm going to try a slightly different approach this time. I'm going to take the 4 on the outside of these square brackets and bring it into the factors of this product here. Now I'm going to think of this whole thing, including that fourth power, as just one of those factors, and this x to the 3/2 as the other factor, so that these two exponents are getting multiplied by that 4. That's what I'm going to do first. So that's going to leave me with this. X squared times y cubed. Now this 4 here is getting multiplied by this 4. And again, I'm using property 5 up here. 4 times 4 is 16. Here, 3/2 times 4 is 6. That's just multiplying that fraction to that whole number. Okay? Now let's keep it going. I have another set of parentheses with a product on the inside and an exponent on the outside, and we can bring that exponent into each part of that product. But then I'm going to have a power to a power in each of those cases, so I can multiply those exponents. 2 times 16 is 32. This becomes x to the 32nd power. 3 times 16 is 48, so I get y to the power of 48 here. And then this x to the 6 is still there. It's just hanging out. I'm not done yet, because when I look at what's left here, I have two expressions, two factors in this product that have the same base. And when I multiply those together, I can use the first of my exponent properties to add those exponents. This gives me x to the 38 times y to the 48. Okay? And that would be the answer for that one. I can't simplify this any further because these exponents don't match, so I can't pull an exponent out. And also these bases don't match, so I can't combine those in any way. That's as good as that one's going to get. All right. All right, now we're on to one that says expand. So when it says expand, usually what that means is we have a product of two expressions and we want to multiply that product out. So there's a couple of ways to do this. In algebra, you learn about a technique called FOIL, which stands for first, when you multiply the first of these two terms together. Outside, these are the outside terms. Inside, these are the inside terms. And last, you multiply the last two terms together. But this particular product has a very specific form to it. If you compare the stuff in this set of parentheses to the stuff in this set of parentheses, the terms appear to be almost the exact same. 2a to the 3/2, 3b to the 5/2. The only difference is that I have a minus in one case where I have a plus in the other. There's a fancy name that we use for pairs of expressions that look like this. We call these conjugates. Then conjugates are basically binomials. This is a binomial and this is a binomial, where the only difference between the two is one will have a plus, whereas the other one will have a minus. Now, the reason we care about these is because there is a shortcut to multiplying this out. In algebra, you learned about something called a difference of squares. If I have an expression of the form a minus b times a plus b, that is always going to multiply out to a squared minus b squared, the first term squared minus the second term squared. And you would get that if you did the FOIL technique, because two of your terms would end up canceling each other out and leaving you with just this. But generally, we want to just know that this technique works and jump straight to an answer where we have this, cutting out that middle step. So this is a difference of squares, which means when I multiply it out, I should get something of this form. So the a here means the first term in each of these binomials. In my case here, I have 2a to the 3/2, and that's supposed to be squared when things get multiplied out, squared, minus 3b to the 5/2 squared. Okay? Now, because I have a product in each one of these things, I can distribute the exponent in. So first I'm going to have 2 to the second power, or 2 squared, which is 4. A to the 3/2 to the second power. Now it's a power to a power, so I multiply them. But when I multiply them, this 2 and that 2 just cancel each other. I get a cubed. Similarly here, minus. Now I'm going to take that 3 and square it. That's 9. B to the 5/2. So when I square it, I also get cancellation, which gives me just b to the 5th. Okay, same answer I would have got using the FOIL technique, but in a lot less time. And especially in calculus, when we're doing limits, in the first chapter, this is a very, very useful thing to remember because we use it a lot. So that's a difference of squares that we're doing there. Okay, I can get these pages separated. A few more examples to do. Oops, just dropped my pen. All right, let's do another one where we're expanding. So again, when we're expanding, we have a product of two expressions. And in this case, I have a single monomial, which is what this guy is called, times a trinomial. It's a polynomial with two variables in this case and three terms altogether. 1, 2, 3. So all I need to use for this one is the distributive property. I'm going to take this 4p to the 1.5 power and distribute it here, here, and whoa, there. Okay? And in the process of distributing, which means I'm multiplying this to each one of these terms, I use my exponent properties to simplify things as I go. So 4p to the 1.5 times this first term. That 4 is the only constant in this whole expression. And this would be called the coefficient for that term. So nothing's happening to that 4. It's going to stay a 4. Then I have p to the 1.5 power. And if there are any other p's to an exponent in this expression, I can use my first exponent property to combine them. I can do that here, p squared and p to the 1.5. When I multiply those, I add their exponents to get p to the 3.5 power. This q has no other q's to combine with in this expression, so it's going to stay a q. Okay? The next term is minus 5.1 p to the 0.5 q to the 1.5. Same idea, but this time I have a constant here, negative 5.1. So that has to be multiplied to this 4, which would give me negative 20.4. Then again, I also have p to a power and p to another power. I can combine those by adding their exponents. 1.5 plus 0.5 is just 2. So that becomes p squared, and then q to the 1.5 is staying put. Finally, my last term here doesn't have any constants, and it doesn't have any p's in it. It's just a q squared. So really, I'm just mashing those things together. Plus 4p to the 1.5 q squared. There's no opportunity to combine or simplify anything there. And that's it. I would call that done. This is not a simplified problem, it's an expanding problem. We're multiplying things out. All right, 2 more to go. So the last 2 problems involve radicals. Now we did talk about some radical properties, but for the work that I want to do here, I actually want to just convert all radicals into rational exponents. It's going to be the easiest way to handle these. So what I'm going to say is rewrite this as 32 x to the 10th over, that's a y to the 9th right there. This is the square root of z, but as a rational exponent, that's the same thing as z to the 1/2 power. And then if I take all of this stuff and I'm taking the 5th root of that, it's the same thing as raising it to the power of 1/5. Okay, that's the exact same thing. So now I can go through and I can take this 1/5 and distribute it to every part of this quotient and the products contained in it. Now, when I take this 1/5 and I bring it to that 32, I have to remember that that means the 5th root of 32. And 32 actually has a nice 5th root. It's just 2. And that's because 2 to the 5th power is 32. Here, I have x to the 10th, and then that's going to get raised to the 1/5 power. I use the same properties that I've been using up until this point. I multiply those powers. 10 times 1/5 is 2, so I get x squared. Down here, same idea, y to the 9th to the power of 1/5. Multiplying those exponents gives me y to the 9/5 power, and that doesn't simplify in any way. That's going to stay put. Finally, z to the 1/2 power, and then raised to the 1/5 power, multiplying those exponents together. 1/2 times 1/5 is 1/10. Now I could convert any rational exponents in this back into radicals, and in an algebra class, oftentimes they'll ask you to do that. The reason why is because if the problem was originally given in radicals, then the expectation is that your answer is given in radicals. However, in calculus, like I said before, rational exponents are actually preferable to radicals because we have some techniques that we're going to learn when we get to this chapter on derivatives that make taking derivatives of expressions that have rational exponents very, very easy to do. So we're going to choose rational exponents over radicals anytime that we can in this class. That's as much as I'm going to do there. One last example, then we'll be done with this video. I want to simplify this guy right here. And we're going to use the same approach as before. I'm going to look for any radicals. There's only one this time. It's a big square root. But I'm going to rewrite it using a rational exponent. So I have p r squared. And that whole thing is being raised to the 8th power. Down here I have 9 p cubed r to the 4th. And instead of writing a square root, I'm going to write it as a 1/2 power. Okay? Now at this point I have a couple of choices as to how to proceed. I could take the 1/2 power and distribute it in right now, or I can work on simplifying the stuff inside the larger set of parentheses first and then wait a little bit to deal with that 1/2 power. I'm going to do that. I'm going to do the latter of those two. So first thing I want to do is take the 8 outside of this smaller set of parentheses and distribute that in. That's going to give me p to the 8th, r to the 16th. And hopefully by now you're seeing where that's coming from. P cubed r to the 4th there. Okay? Now at this stage, I can start simplifying things. So I have p's in my numerator and denominator, r's in my numerator and denominator, and I can start subtracting those. So subtracting the exponents, because that's the exponent property we'd be using. P to the 8th over p to the 3rd, I do 8 minus 3, which gives me a positive 5. Remember, when you do that, when you do the subtraction, the end result always lands in your numerator. And then in a later step, if you get a negative exponent from doing that process, you can shift it into the denominator by resolving that negative. R to the 16th over R to the 4th would be R to the 12th. It's positive, so it doesn't need to move out of the numerator. And then I still have just a 9 down here. Notice that I only have p's and r's showing up in one location now because I've done some simplifying. This is still to the 1/2 power. Now I want to bring the 1/2 in and deal with everything in here. So in my numerator, I'm going to get 5 times 1/2, which is p to the 5/2. Here, I'm going to get r to the 12th to the power of 1/2. Multiplying those, 12 times 1/2 is just 6. R to the power of 6. Now 9 to the 1/2 power. I'm not multiplying those because this 9 is not an exponent like the 5 and the 12 were. It's just a constant. So I'm literally taking 9 to the 1/2 power. But remember, that means the square root of 9, which is 3. We know that one. And that's it. All right, so this was just a collection of examples where we're expanding and simplifying expressions using those exponent properties. Again, the assignment is going to look just like this. It's going to have different problems, but you're using all of the same techniques. So hopefully that was enough to get you started.